Hello everyone, my name is Michael Horn. This is the second video I've uploaded, and in this video I will be walking you through the process of how to derive dynamical equations for a two gravity drain tank system that are connected in series. A PI controller will be adjusting the flow in the first tank to bring the liquid level in the second tank to whatever desired set point we want. And to do this, we're going to be using the Fundamental Theorem of Calculus on the integral component of the controller and identify it as an intermediate state variable to facilitate the computational simulation. It sounds like a lot of words, but I promise we will break it down and it will not be that awful. We will also be starting on this iPad. We will work through the problem there, identify all of our variables, and then like the other video, we will go into Google Colab and code out the simulation to find our desired set point. So okay, let's get started. So as you can see, I've added the two tanks here, and just like our last video, we are going to draw out this process so we get a mental understanding of what is going on. So I'll make this orange. We will have Q going in. And then here, you know what, we'll drop this down lower. So there's going to be, before I draw Q1 going into Q2, there's going to be a small outlet hole here, and which it'll be flowing out of. So this will be Q1, this will be Q out. Okay, so our cross-sectional area here, which we will label AH. From the problem statement, we know that this is AH equals 0.1 meters squared. We also have this cross-sectional area of the tank, and this area is equal to 1 meter squared. Finally, we have the liquid level, just make blue. Then this is going to play a big part because the whole point of this problem is actually finding the desired height. So H1 and H2. So this is what our total system will look like, and we can move on from there. So just like in the previous video, we are now going to start to derive some equations. Sorry. Okay, so this first equation we are going to have the height, dH, is going to be changing over time. That's why we have dH dt. And this is going to be equal to our Q in minus A out radical 2GH 1/2. Now, this is just like the equations we had in the last problems. So from here, we can also make a second equation and third equation accordingly if we needed it. So you could tailor these H values, I'll circle in red. You could make the subscripts 1 and 2. So for example, you could do A d H1 over dt equals Q in minus A out 2GH 1/2. And then you can even go furthermore and say, okay, well, I want Q2. You can do, okay, well, I want dA dH2 over dt equals Q in minus A out. Same thing to H8, but this is H2. Now, from here, we are actually going to derive the dynamical equations and see how that PI controller can actually adjust the height of the second tank's liquid to your desire. So now that we have these two equations, we are able to actually isolate what Q in is. And if you watched the previous video, I'll give it a kind of a quick summary. The controller is based off a error value, and that error value is equal to HSP, the height set point, minus H2 multiplied by the controller KC, controller value. So here, what we're going to do is do Q bar minus this KC times HSP minus H2. Now here, the only issue with this is that this value right here highlighted can have a offset, and to account for this offset, we're going to use the proportional integral PI controller. So we are going to add an integral here, in which the integral will help kind of massage out that proportional issue. This is actually a plus, I'm sorry. We're going to do add ki for the integral, and that integral is going to be from over starting at 0 to t, the time that we want to go to, and then it's going to be the same thing, hsp minus h2, and this is going to be with respect to tau. So now what we're going to do, I will highlight, we are going to take this first equation and take this second equation, and we are going to plug this into there to create one large equation. So I'll get rid of these highlights. And just for the sake of being a little more concise, this value right here, we're going to set as E. So I'll kind of make that known. Okay, so we will have Qn equals 1 over A times Qn. Now, like I said, we're going to take this right here and just throw it down there. So we will have plus Kc, and like I said, we're just going to call this E, plus our proportional control integral proportional integral controller. It's a mouthful. 0 to t, height set point minus height 2 with respect to tau, and at the end we're going to Q1. So now you might be thinking, well, where does the fundamental theorem of calculus come into play? But before we do that, we have one more equation to write, and that is going to be Q. I realized I made a little mistake here, so let's fix this. This is not Qn. This is dH1 over dt. I realized that when I went to write the second equation. The second equation is dH2 over dt, and that is equal to 1 over A over Q1 minus Q2. Now, like I said, where does the fundamental theorem of calculus? We'll write this, FTC. Now, this FTC is going to be the the derivative of the error with respect to time. So what that's going to look like is d over dt is going to be equal to our height set point minus h2. So now that we have identified the fundamental theorem of calculus and how that applies, we're going to combine this even more. And so going to the next page here, so dH1 over dt is now equal to 1 over the area times times Qn plus Kc, and now this E that we just derived from there. So now we can do plus our control integral, and instead of this big nasty mess, we will have just this E value minus Q1. And then we will just, so it's more organized, we'll have our second equation, which is height 2 equals 1 over the area of Q1 minus Q2. And yes, so that is the two equations that we have right now, and we will move on. So now we're looking at all of this calculus, and you could be asking, well, you know, what are we actually going to use? What is important here? What is not important? And I want to highlight the three things that we are going to use once we actually move over to Google Code Laboratory. We're going to be using this equation, and this equation. So I will try to get these onto one page. Copy, paste, nice. All right, so we now have these three very, very important equations. So important that I'm going to highlight them in yellow. This one, and this one. These three are the three main equations that we are going to need when we move over, and we are going to plot these in Google Colab, and see what outputs they give us, and what we want to set that Kc value equal to if we want a certain height of liquid. All right, so I have opened up Google Colaboratories, and just like in part 1 of this explanation, we have to import all of these. So we're just going to take it over. And just in case you didn't see the first video, this is importing all of the arithmetic that the code is going to need to complete all of these calculations. So to start, I am going to learn from the mistakes I made in the previous video, and I'm going to define all my variables first. That way I have no undefined variables. So let us start with gravity, which is going to equal obviously 9.8 meters per second squared. So we are on Earth. Next we will have our cross-sectional area. So this green circle, which in the problem statement was listed as 1 meter squared. Wait, sorry, I'm forgetting units of area. Yeah, meters squared. I don't know what I'm thinking. Sorry. All right. Next, we're gonna have our cross-sectional area, which was listed at 0.1 meters squared. Next, we will go into the Q in naught, which was listed at 1 meter cubed per second. And next, we will have our H naught. Now, our H naught is going to be the equation that we derived in the first video and this video. So that's going to be your Q in naught just above. We are going to take that, divide it by AH. And now all of that is going to be squared and then divided by 2 times your gravity value. Okay. Now next, after H naught, we are going to move into the height set point, which is going to be equal to 20% more than the original H naught, which was listed in the problem statement. So H naught. And then we will have Kc like we did last time, which is going to be our controller gain. We can set that to really any arbitrary number right now. We can do 10. And we will label it so we know what's happening, controller gain. And then we will have Ki, which is our controller integral, which we will set to 0.1 controller integral. Okay. Now, obviously we have all these variables, but what do we actually want it to output? We want to output H naught and HSP, so we will put H naught, comma, HSP. All right, great. So this is all of our variables defined, ready to be plugged into our solution equation. Great, so now we are going to add a line of code here, and we are gonna set our variable. Again, we can name this whatever we want. Let's go with blue. First word that came to my mind. And we are going to set this to, just like we did in this, reconnect here. Okay, just like we did here, we are going to use this same equation, AH times NP square root of 2 times G. So let's do that. AH times NP square root of 2 times G. Now, after this, we are going to have to define, just like in the previous one, the right-hand side along with t and the vector. So we will define right-hand side, t, because time is still, everything's dependent on time in these equations, and vector. Colon. Now here, last time we did h1, 2, and 3. This time we're going to do h1, h2, and then this, as you can see, right Oh, I'm sorry, I had it up already. This variable, we're going to do eInt as our third vector, so they are able to be plotted on the graph. So let's type that in. So we have h1, h2, and eInt. So next we have to actually set this equal to VEC, sorry. And then we are next going to set all of our Q values. So Q1 and Q2 need to be defined. And these are going to be set as blue times NP square root of Q1 is going to be associated with H1. And then same thing, blue NP dot square root of H2. Now, along with this, we need to define our, not the uppercase squiggly looking E, like the lowercase e that we wrote right here. We have to define what that is, and that is height set point minus H2. So let's type that in, E equals HSP minus H2. Now next we are going to want to create our equation for Qn. And the way that we would know this was from these highlighted equations above. So we're going to do Qn is equal to Qn naught plus our Kc value. Did I make it capital? No, lowercase. Okay. Kc times E, and then plus Ki, the integral, and that is going to be multiplied by eInt. Now, the E and eInt variables are so similar, we're going to want to ensure that Google Colaboratory knows that they're different. So the way that you would do that would be eInt plus equals E. That way it knows they're not the same. So now you might be thinking, well, what actual numbers do we want it to return? And that's exactly the step that we are on. So the things that we want this to return are the difference in Q0 and Q1 divided by the area. Q minus Q1 divided by A. That's our first. Our second will be Q1 minus Q2 divided by the area. And then finally, we want the output of our actual error, E. So now the next step is actually creating our solution equation. And so the way that we are going to start this is by typing res equals solve underscore IVP. Now this is going to look a lot like this one, which we've done before, but obviously there's going to be some minor differences because we will be working with a PI controller. So now it's going to say we're going to be solving that right-hand side first, and then we're going to do 0, 10, and then next it is bracket. I couldn't find the bracket. H0, 0, close bracket, comma, and then we need our method, which is going to be the same thing as the previous video, which is going to be do followed by dense underscore output equals true. Why did it do that? Dense output equals true. What in the world is going on? These parentheses, I don't understand them. Okay, so that res equation should be good. And then next we need to define all of the plots. Like here we have H1 plot, H2 plot, H3 plot, but in this situation we're gonna have H1 plot, which is the same, H2 plot, which is the same, but now, like I said, we're gonna be dealing with error, so this is going to say eInt, and this is going to all equal res dot sol eplot. So now we are actually able to move into the fig plotting and deciding the width and height and color of our plot. So actually I went through my code, wanted to double check before we actually started plotting, and I realized when I was typing in this tendency, I completely forgot to type in and defined actually t-plot and the tendencies. So just like we did here, we're going to have to define our tendencies and our t-plot. And we actually want to use the same numbers here since it's a similar system. So we'll just take that and throw it in here. And now we want to actually plot this on a scatter plot. So it is going to be very, very similar to this. So just to save us time, we can copy this in, and I will still walk you guys through what it actually means. So let's get rid of this because we only have H1 and H2 this time. So fig equals make subplots. That is going to be us actually making the plot in Colab. And now we have to make the scatter plot, x equals t plot, y equals H1. That is going to be our first line. And then you will see a second line that is H2. And now the last line you see fig.update layout. This is simply for cosmetic purposes. It'll allow us to adjust the width, height, and the background of the plot. So now let's play with this code and see how it ran. I doubt it runs correctly the first time, but you never know. Looks good so far. It's thinking. Okay, so we have a very stable and straight line. And now together, let us, I wish this would go away. There we go. Let us adjust this KC and KI. Now they are very dependent on each other. So let's try to find, let's say we do 1 here. Let's see what changes. The line is still very straight. Now what if we do 0.1 and we make this 0.01? Still a very straight line. I am honestly trying to make it outrageous so we can tell that it can be unstable, because that's what we don't want. So everything is becoming very straight. Let me take a moment and figure out what is going on. Alright, so I did find the issue. Right in this return function, we were returning the wrong value, change that, and so now you can see these two lines that are squiggly. Obviously the straighter line means more stable. So let's mess around with this. If we start out with, let's say, 100 KC value. Oh. I think that's honestly so big it won't even let me do it. Let's run 5. There we go. Okay, so you can see at the beginning it's very, very unstable at the beginning, and instability. You know, obviously on this computer doesn't seem like it's that large of a deal, but in the real world, an unstable chemical reaction can lead to a lot of terrible and unsafe consequences. So you really want to find the balance between this Kc and Ki value. So let's say we have our value at 5. Let's check Ki. Let's see what happens if we change that to 2. What happens? Also not even allowed. So let's make this small. Let's make this 0.001. And let's make Kc 1. Let's see what happens. Still a lot of squiggles in there that you really don't want. So the trend that I'm starting to see is that, okay, well, I want this Ki value to be C, and I want this Kc value to be also very, very close. So let's try what was I just at? 0.1. Let's do 0.0. Let's do 0.05. Wait, did I just do 1? I think I just did 1. Let's do 0.1. Okay, so a lot less oscillations. I shouldn't be using the word squiggles. A lot less oscillations. Let's see what happens if we drop it down to 0.05. Now, we're getting too close to the Ki value, so the squiggles are getting more drawn out. So we want them to stay as compact as possible. So that 0.1 value seems to be a very, very balanced solution to our issue. So I appreciate you watching. Again, my name is Michael Horn, and this was a step-by-step basis for two gravity drain tanks connected in series with a PI controller that we worked through, and finding the correct balance between the KC and the KI factor.